In our last chapter, we focused on motion in general. In this chapter, we're going to focus on how forces affect motion. So a force is a push or pull that causes acceleration. So remember, to accelerate, we have to change our velocity. In order to change velocity, we either have to speed up or slow down, or just change direction, or of course, a combination of those would also work. Force is going to be a vector quantity, which means that we can represent it with arrows, as I have down here. And those just mean that force has both a magnitude and a direction. And we're going to measure force in newtons. 1 newton is the force that causes a 1 kilogram mass to accelerate at a rate of 1 meter per second squared. Net force is the overall force that's acting on an object when we combine all of the forces that are acting on it. So for example, if I have a force of 5 newtons in one direction and 5 newtons in the opposite direction, that would equal a net force of 0, and we consider those to be balanced forces. So imagine two people pushing on a box with equal amounts of force on each side, the net force would be 0. We can also have unbalanced forces. So if I have 5 newtons of force in one direction and 5 newtons of force in that same direction, they're going to add together to make 10 newtons in that same direction. So that's considered unbalanced, and it's going to cause our object to accelerate. So in this case, our object would speed up. So imagine a box on a floor, and instead of the people being on opposite sides of the box, now they're on the same side of the box pushing with the same amount of force. There are several types of forces, and one type of force is friction. This force is always going to oppose motion of objects that are in contact with one another. There are several types of friction. There's static friction, which is going to be for objects that are not moving. So like my board right now is sitting in the tray, and there's friction between the board and the tray that's causing this object to not move. There's sliding friction, which is when if I apply enough force to this board, I'm going to be able to slide it over when I'm done. There will be friction between the tray and the board still, but there will be less friction than there was when the board was just static or stationary. Rolling friction has even less friction, and that's just when an object is rolling. So think about if you have something heavy that you're trying to move, you put it on a dolly that has wheels on it, because then there's less friction between your object and the ground. And then lastly, we have fluid friction. Fluids are not just liquids. Fluids are also gases. So anytime I have an object that's moving through a fluid, so through a gas or a liquid, then that's going to be considered fluid friction. And an example of that is air resistance. So anytime an object is traveling through the air, which it always is, there is fluid friction in the opposite direction of our object's motion. Another type of force is gravitational force. Gravity is an attractive force between any two masses. So any two things that have mass, and all objects have mass, have a certain amount of gravity between them. So there's gravity between this board and myself. I have mass, the board has mass. There's an attractive force here. However, because the board and myself, our masses are not incredibly different, I'm not going to actually feel attracted to the board, and vice versa. When an object falls, or even just when an object is sitting on something, like right now, gravity is pulling this board down to the floor, there is always, or usually, an upward force that's balancing out that downward force of gravity. So that could be air resistance if my object is falling, so gravity is pulling down, air resistance is pushing up. And another type of upward force that we have is called the normal force. So right now my board is sitting in the tray, gravity is pulling it down, but there is a normal force coming from this chalk tray that is opposing that and pushing upward on my board, which is why my board doesn't just fall right through the chalk tray, or it doesn't fall right through the floor, or it doesn't fall right through the surface of the ground outside. So here I have an inclined plane or a ramp, and I have a box sitting there. and I've drawn some force arrows for us. So first of all, the force of gravity is pointing straight down, as it always does. The normal force is pushing up against my box. And then the frictional force is opposing the motion of my box. So my box is moving downward. So friction is always opposing that, so it's going to be in the opposite direction. So more about those objects that are falling. Some of this is review from last chapter. So with falling objects, we could have free fall, or we could have projectile motion for our purposes. So when an object falls, it is accelerating due to gravity. And so we saw that in our book, for example, when the pebble was falling throughout the well, and it was getting faster and faster, so it was accelerating. We call that free fall. So this top picture here, we have the ball falling, and we see that those arrows are short and then longer and then longer. So from here to here, I've got free fall going on. My object is accelerating. Eventually, though, the air resistance that's acting upward on my falling object is going to equal the same force as gravity. So my object will not accelerate anymore. It will still travel downward, but it's going to travel at a constant velocity, which we call terminal velocity. So again, falling, getting faster and faster, but then my arrows are the same length, indicating they have the same velocity or the same speed, and therefore my object has reached terminal velocity. Now, instead of just dropping the ball, if I actually push the ball forward, as is indicated here, my ball is going to fall in a curved path because of that initial forward velocity, and we call that type of motion projectile motion. So some scientists that dealt with forces in motion are Aristotle, Galileo, and Newton. Aristotle, just like we saw earlier in the year, was wrong about something science related. And in this case, he's wrong because he thought that force is required to keep an object moving at the same constant speed. So he thought that if you wanted to keep going the same speed, you got to keep applying a force to it. Galileo thought of it in a little different way, or actually in an opposite way. He said that if there is no friction or other force that's opposing the motion of an object, then it's going to maintain its constant speed. So this is the idea of if you kick a soccer ball and it's rolling through the grass. Aristotle said you have to kick the ball again if you want to keep it going at a constant speed. Galileo said you don't have to kick the ball to keep it going at a constant speed. What's slowing it down is the friction between the ball and the grass. And Galileo is the one that's right about that. An object continues moving until some other force ends up slowing it down or changing its direction or speeding it up. So Newton built on Galileo's work. He agreed with him. And he ended up defining mass and force for us, and he came up with our special laws of motion. His first law of motion is the law of inertia. Inertia is the tendency of an object to resist a change in motion. So think of this like objects are lazy. Think about how when you're laying in your bed in the morning and you don't want to wake up, you are being lazy. You want to keep sitting there. And then the same is true if you're up and you're walking. It's more difficult for you to stop walking once you have started to walk. So inertia is the reason that we wear our seat belts, because we are traveling forward in our car, and if something stops the car or if the brakes stop the car, you in the car are going to keep moving because you don't want to change your motion, and your motion right now is moving forward. So the seat belt helps to stop that. You also see inertia if you have something sitting in your car and you turn and the object in your car wants to keep going forward, or it wants to turn in the opposite direction. So that's also the idea of inertia. So objects in motion are going to stay in motion. Objects in motion stay in motion. Objects at rest stay at rest, unless we make our net force not equal to 0. So if I have some sort of force like friction, for example, or if you personally stop the ball with your foot, then your net force is no longer 0, and so your object that's in motion is going to change its motion. It might stop. Or your object at rest is no longer going to be at rest. It's going to start to accelerate. Okay, our second law of motion is summed up with an equation, which is force equals mass times acceleration. Force is going to be measured in newtons, mass is measured in kilograms, and acceleration is measured in meters per second squared. So here's an example. What is the acceleration of a 26 kilogram box being pushed with 32 newtons of force? Here's my original equation. I've circled what I don't know, which is acceleration. I decide that I need to divide both sides by m, so m over m cancels out or equals 1, and acceleration is going to be equal to force divided by mass. I plug in my force and my mass, and I get 1.23 meters per second squared. So this whole idea of this equation is basically that if you increase the force on an object, like if you apply more force to that soccer ball, that's going to increase its acceleration. And if you increase the mass of the object that you are trying to push or pull, you're going to end up decreasing its acceleration. Another way to think about this is with a very similar equation, which is weight equals mass times the acceleration due to gravity, which we represent with the letter G. So weight and mass are not the same thing. We talked about that earlier in the year. Weight relies on gravity. Mass does not. So weight is actually a force. So we're going to measure that in newtons. Mass we still measure in kilograms. And then our acceleration will still be measured in meters per second squared. But since it's the acceleration due to gravity, and that is always the same, we need to memorize that g, or acceleration due to gravity, is 9.8 meters per second squared. And our final law of motion from Newton is his third law, which is about action-reaction forces. This is typically summed up as every action has an equal and opposite reaction. So if I push into the board here, the board is going to push back on my hand. Or if a swimmer, for example, is swimming down to the end and is going to make the turn to come back, he or she is going to kick off of that wall as hard as he or she can, because the harder he or she kicks on the wall, the more that the wall kicks back on the swimmer, and that's going to help to accelerate him or her forward so that he or she can win the race. Action-reaction forces act on different objects. So in our example that I just gave, the swimmer kicks on the wall pushes on the swimmer. So we don't say that those forces cancel out or balance like we did before, because when we talk about balanced forces, we're talking about two or more forces on the same object. So in that case, we were talking about a box. You know, one person pushing on this side of the box, one person pushing on this side of the box with equal amounts, then that would be balanced forces. But in action-reaction forces, they are not acting on the same object. So my swimmer is kicking on the wall, and the wall is pushing on the swimmer. They're not acting on that same object. So think of it as A acts on B, and B acts on A. They are acting on each other. So what I'd like you to do is to try these two problems. So in this first problem, I have a box, and I have some force arrows there, indicating that there's a 40 Newton force downward, 40 Newton force upward, 30 Newton force to the right, and 20 Newton force to the left. So I want you to determine the net force based on those forces. And then for your second problem, I have a box on a table, and I want you to determine the force due to friction and the direction that friction would be acting in this picture. So the information you have received is that the box is 35 kilograms. The acceleration of the box is 6 meters per second squared, and it has an applied force, meaning someone has pushed on the box with a force of 300 newtons. So what would be the force of friction that the box would be experiencing, and in which direction would the friction be? So draw an arrow for the friction.